Hi there. So today what I'm going to do is talk a bit about Mohr's circle. Now, people who have me in a class know that I treat Mohr's circle as the kind of thing where, yeah, it's a great concept tool. Do I use it for much on a daily basis? Do I use it for much whenever I want to look at something? Well, typically not. Let's put it that way. There are instances where Mohr's circle is valuable. I know that civil engineers use it for a couple of things, especially for things like soils. That comes to mind immediately. And it can make a nice, quick and dirty kind of tool to come up with a general answer if you want a general answer. Now, that means we need to know a little bit about how to draw it. And it just so happens that today, this very day, I just got done looking through a pile of homework assignments. Yeah, that's part of my job, go figure. And go figure, they also had a bit of an issue, almost about half of them, little subtlety with drawing Mohr's circle, okay? And I want to talk a little bit about how we can draw Mohr's circle correctly and consistently. So this way we can set ourselves up for most success, right? So I've got a state of stress. I've got numbers on this just because I know people like to see numbers, okay? Do the numbers themselves matter? No, not at all. They really don't, okay? They can be whatever numbers they have to be, whatever numbers they are to work, okay? So in this case, I've got sigma y at 6 ksi, tau xy at 4 ksi, sigma x at 10 ksi, and I want to plot Mohr's circle. Okay. Now, the trouble is, right now, in this coordinate system, I've got a positive shear stress. How do I know? Well, I can look at the positive x face, right? That's the one where the positive x direction would be coming out of the face. And it turns out that's the face on the right. The way I drew my coordinate system is the way we draw a coordinate system probably at least 3/4 of the time. And sure enough, I've got a positive y force on that positive x face. And I can go around to any other face I want, and I'll get a positive force on a positive face or a negative force on a negative face. And when I tell my classes all the time, you treat it like multiplication of numbers, right? Positive plus positive, positive times positive, I should say, gives you positive. Negative times negative gives you positive. Hey, look, no matter which face I look at, I've got a positive result. But the thing is, whenever I draw a Mohr's circle, I've got to have one of my normal stresses plotted with a shear stress above the axis, which we always think of in our brains as positive, and one below the axis, which we always think of as negative. We have to lose that positive-negative connection. We can't think of us having the vertical direction be positive or negative, right? What we have to think of is the couple that's being applied to those faces. I'll explain what I mean in a second. So I've got some axes that'll be handy for Mohr's circle. And I know I'm going to need to have 6 ksi for sigma y and 10 ksi for sigma x. So let me just mark those off. I'll put 10 ksi over here. Sorry about the movement there. I'll put 6 ksi here. And because I know a bit about Mohr's circle, and yeah, the scaling's kind of off, that doesn't really matter. Okay, because I'm not going to take out a compass here. This is not going to be anything resembling a circle. This is going to be a bit of a freehand circle. So any resemblance to a real circle will be purely coincidental, right? But I'm going to put my average normal stress in there at 8 ksi, because I can do that math in my head. 6 plus 10 is 16, divided by 2 is 8. That's the average normal stress every time. Okay, so the x point has to get to 10 ksi. How do I figure out whether that point goes above or below the horizontal axis, right? Notice I've got these arrows above and below in lieu of a plus or a minus. I've got above a clockwise arrow, and below I've got a counterclockwise arrow, okay? What's that going to do for me? Aha. So, what that's doing is I can take this setup, and the stress block has, it's not exactly square, but we'll live with it. And I'm going to do something a little bit funny. I'm going to insert a shape here. Let's go with a rectangle. And, hey, apparently it doesn't want to insert a rectangle today. Aha, there we go. And I'm going to insert a rectangle like that. Because right now, I don't care at all. Sorry about that. I don't care at all about what's happening in the y direction. I care at the x direction. And notice, on these x faces, I've got this arrow on the right for my shear stress, and the other arrow on the left. The arrow on the right is going up, the arrow on the left is going down. That's a couple about the center of the stress block that's spinning counterclockwise. That's how I know where to put this point for Mohr's circle. I've got a counterclockwise couple on the x faces. I said counterclockwise was below the way I drew my number, the way I drew my axis. So my x point is going to go, and I said that was 4 ksi. That was 4 ksi. Magnitude of 4 ksi. It's going to go down here below the horizontal axis. You want to call it 10 minus 4 just because we can put a negative on that for the sake of having something in there. People like seeing negative for that. But yeah, and here is what we could call minus 4 ksi. The y point is going to get plus 4 ksi. How do I know that? One, well, it's always opposite, right? That's the easy, cheesy kind of way. The other way, so if I take this thing here, let me pick my rectangle real quick. I'm going to rotate it by about 90 degrees. I'm, of course, going to have the rectangle be too big because my stress block is a little bit squished, right? But notice, now I've blocked out the x couple, okay? Because I don't care about the x couple anymore. What I care about is the y couple. And sure enough, that y couple, well, it's going clockwise. I knew it had to because it has to be equal and opposite. Otherwise, that stress block would have been spinning. We know it isn't. Otherwise, it's not in equilibrium, right? We know we have equilibrium. So what I can say then is my y point at 6 ksi for a normal stress is going to get 4 ksi above the axis, above the sigma axis, if you will, because that's where I have the counterclockwise couple living. I put my y point here. Y lives at 6, 4 ksi. And then I would draw a circle, right? Because I'd have certainly a diameter connecting this, and the diameter would go through 8 in theory, and that's not totally horrible, right? For a freehand, yeah, I kind of curved it a bit, so I'm cheating, whatever, right? I'm not using a compass or a straight edge, so I'll let myself get away with it, right? And then I would draw a circle, which looks a little bit like this, and I'm going to take that and walk for a freehand circle. Thank you very much. And sure, I'd have my maximum principal stress here. Here's sigma 1. My minimum principal stress in the plane here. My maximum shear stress in the plane there, corresponding to the 8 ksi axial stress. And certainly, if I want to draw in some angles, I'll use green for these. This angle here would be twice theta p. Looks like that's counterclockwise or a positive angle. And looks like 2 theta s lives here. Right? If we use the equations for theta p, we'd find that theta p was positive. Sigma x is bigger than sigma y. And that's the denominator part is sigma x minus sigma y over 2. Shear stress was positive. Therefore, I should have a positive number inside the inverse tangent. I should get a positive angle back. Well, there we go. It's supported by Mohr's circle because I drew it this way. If my x point were above that horizontal axis, I'd have a problem because then I would need a clockwise rotation to bring it down to the horizontal, right? I'd need a clockwise rotation as opposed to a counterclockwise rotation. Oops, right? That's bad things there. So that's how we plot in this situation. Okay, let me illustrate a little bit further with a second example. And we're going to change around the units. It's going to be MPa instead of KSI. Big deal. All right, they're just units. We can work with those. And what I've also done is I've flipped the sign on the shear stress. Now my shear stress is negative because if I look at my right-hand face, and now I forgot a coordinate system when I set this up. There it is. That's all I need. Right, same XY coordinate system as the previous block. I've got that right-hand face, still the plus x face, now has a negative stress on it. Aha, right? Or negative force, I should say. That means it's a negative shear stress. Okay, well, who cares? It's not really that important. The other thing I've done is I've got plus 40 MPa for sigma y and minus 60 MPa for sigma x. Okay, so I actually have two opposite signs. So if I go down here, I know I'm going to need something like, oh, let's go 20, 40, 60, 60 MPa, oops, I wanted 40 MPa. That's negative 60 and plus 40. Hello, eraser. Okay. We're going to give this thing one last chance in a second. After I draw this in. Minus 60. This is 40. I'd love to make that 60 disappear. There it goes, right? Sorry about the technical difficulty. Sometimes it happens. Right? And I'm going to have 50 MPa. I'm going to need 50 MPa above and below. We'll split that. There's plus 50. Minus 50. Okay. So now I want to plot my X point, which was the negative 60 MPa. Well, notice, again, if I go back here, I insert my shape again, because I like the way that worked out personally, right? And I'm going to do it the wrong way first, but that's okay. I'll just spin it. And I'm not going to think about sigma y and tau xy for the time being. Or I'm not going to think about sigma y and tau xy on the top and bottom. I'm going to think about sigma x, right? I'm going to set myself up to look at this. And now I have this couple exposed. This is the couple that's sitting on the x faces. This is the couple direction that I plot with sigma x. Well, this is a clockwise couple, isn't it? Clockwise, I said, was above the axis. Sitting right there on the bottom of our screen right now. So that means I need to plot my x point at minus 60 MPa and plus 50, if you will, right? My x point sits at minus 60 and plus 50, and I'm going to move that because I have the very strong impression that when I go to freehand in my circle, I'm going to go right through where I drew that the first time. So my x point is at minus 60 and 50 MPa, and now my y point, I go back to this, my y point, let me drop this, let me pull this thing up a little bit and pull this down. Now all I can see is the couple on the y faces, which is counterclockwise, right? And my tensile y stress. So this is why I have to plot the counterclockwise below the axis shear stress point with y, because y faces have a couple that is in the counterclockwise direction, and we said we plot that below the axis. That's all. So now what we're going to do is we're going to connect our points, right? Our average normal stress should have been around 10 MPa, negative, because I got minus 60 plus 40 is minus 20, divided by 2 is minus 10. Again, for something freehand, I'm not upset with this result. My Mohr circle, for variety's sake, let's put it in blue this time. And this is going to get dicey. Goes around, goes around, goes around. Around, around, around. That's a win again. And here we are with a nice free-handed Mohr circle, at least. If we had a compass, it'd look a little nicer. But here's what we wind up with, right? We're going to wind up with a principal stress. Looks like this is sitting at about negative 70-something MPa. This other one's sitting at plus about 45 to 50 MPa. My maximum shear stress is probably about 70-something MPa as well, 75 or so, right? So this is how we get those points listed. And again, if I wanted the angle to the principal planes, well, here's 2 theta p down here. Here's 2 theta s here. And one more time thinking about that angle that we had, right? I have sigma x minus sigma y over 2. Let's go in the numerator first. I kept going in the denominator first. Let me go in the numerator first. My theta p equation, the inverse tangent of tau xy in the numerator. Well, tau xy is negative. We said that. Sigma x minus sigma y over 2, well, sigma x is negative 60, sigma y is 40. That's a negative. I'm going to have a positive value for the inverse tangent. Well, sure enough, that means counterclockwise rotation again, and that's what we get again. Okay? So this is why we have to plot in that way. If you mess up the way you plot your points, if you put the x point below in this case instead of above that sigma axis, your circle is going to say you need a clockwise rotation where your equations say counterclockwise. That don't work so well, right? You have to make sure to have those points in the right way. And the way you choose whether to go above or below that sigma axis all comes down to that couple acting on the faces, right? This is the y couple because it's the one that's on the y faces. It's the two arrows on the plus and minus y faces. This other couple, if I go back to here, this other couple is my x couple because it's on the plus minus x faces. And this again is how we know which couple to put where, which point to put above and below Mohr's circle. All right, any questions? Fire away. Thanks a lot.